We've looked at how much energy is associated with vibrations. Let's look now at how much energy is associated with rotations. Classically, the rotational energy of a molecule is described by the kinetic energy of the angular motion, where the moment of inertia I and the angular frequency take the place of the mass and the velocity in linear motion. Once again, since we're dealing with microscopic particles, we have to describe this motion quantum mechanically. Quantum mechanically, the energy of rotation depends on the rotational quantum number J and the rotational constant B, which is a function of the moment of inertia. The quantum number J can take on values starting at 0, 1, 2, and so forth in integer values. We can see that, unlike in vibrations, when J equals 0, there is no energy in rotations, and thus the molecule does not have to be rotating. In vibrations, the lowest energy vibrational state, the ground vibrational state, has an energy 1/2 h nu associated with it, and thus molecules are always vibrating. The set of rotational energy states starts with J equals 0 as the ground state, J equals 1, J equals 2, J equals 3, and so on. When I add light to my molecule, when I radiate it, I can absorb a certain amount of that electromagnetic radiation and cause my molecule to begin to rotate. The amount of energy required to cause this rotation is the difference in energy levels from where I started to where I ended up. This amount of energy is given by the quantity 2J plus 1 times Planck's constant times the speed of light times the rotational constant. The moment of inertia of my molecule, which is related to the rotational constant in a reciprocal relationship, depends on the reduced mass of my molecule. For a diatomic, the reduced mass can be calculated as the mass of one molecule times the mass of the second molecule divided by the sum of their masses, and the bond distance R between the atoms. Mathematically, the moment of inertia is equal to the reduced mass times the distance between atoms squared. So the moment of inertia increases when the reduced mass increases, or the mass of each individual atom increases, and the moment of inertia also increases when the distance between particles increases. So larger molecules have larger moments of inertia. Notice that a larger moment of inertia translates to a smaller rotational constant. A smaller value of the rotational constant B will lead to smaller spacings between rotational levels and thus less energy required to make the molecule rotate. This is somewhat counterintuitive because larger molecules are easier to begin rotating than smaller molecules.